looking at chlorinated solvents, most specifically TCE, trichloroethylene, which has been a problem in the environment because it's persistent and it was used in industry as a degreaser, as it has solvation properties and it can take grease off of metal. And so when it was disposed of in industry, it wasn't disposed of correctly, and now, as you can see in these maps here, it's kind of found all over the country in groundwater samples. And so ways to remediate this have been like, one of the ways is called air sparging, and what you do is you pump the water to the surface and it goes through this column, and air is like shooting up through the column as your water's coming down, and it causes the trichloroethylene to come out into the gas phase and get out of your water. But that's really energy expensive and also economically expensive. And so another way that you can remove chlorinated solvents from your water is through catalysis, specifically with palladium. And so you can't just throw palladium into a water sample, though, because palladium can be poisoned and therefore not work anymore. And palladium can be poisoned by reduced sulfur species that are found in the water. And so what we needed to do was protect our palladium somehow. And so that's where Ozorb comes in. And Ozorb is this novel material that it absorbs organic contaminants, but it leaves out water and ionic species, any really polar species. And so, just like some of these pictures are showing how in acetone, Ozorb swells, and so pretty much all of these are just showing how Ozorb swells. But what we did in this project specifically was we took a palladium catalyst and we put it inside the Ozorb. So Ozorb is kind of acting as a protective box for our palladium nanoparticles. And so what this means is the Ozorb sucks in the TCE and then interacts with the palladium once it's inside, and then it can come back out of the Ozorb. And so you are catalytically remediating your chlorinated solvents, and this is a much more economically and energy efficient way of doing this. And so you're probably thinking, like, why aren't we doing this right now? Like, this should be going on. But the barrier that's in the way of getting this going on a large field scale is the fact that palladium is poisoned by sulfur species, and it's kind of been a back and forth of, okay, so how do we solve this problem of the sulfur poisoning? And so what we did in my experiment here, I would take this little reactor, and it's sealed, and I would spike it with 30 parts per million of TCE. And then, let's back up a second. I would take this and I would put water into it, and I'd put my palladium Ozorb into it, and I'd have hydrogen going into it. Because another part of the catalytic reaction is you need to have hydrogen in this, it needs to be saturated with hydrogen. So once the environment was completely saturated with hydrogen, then I would dump in my TCE, and then from there I would take water samples. I would just pull them out through a syringe in the top here, and I would take water samples at 10, 20, 30, 45, 60, 120, and 180 minutes. And then I would analyze those samples by GCMS, and what I did here was I just plotted them, and I would see the degradation in TCE levels. So this is my concentration of TCE versus time. And if you're like looking at this and like, oh my god, why does it go back up? It's because I did it for 3 hours and then I respiked it and did it again to see, are these reproducible? Is it going to continue working? And so the first thing I needed to do was prove that catalytic activity was happening. And so my controls were, I used palladium Ozorb as my experimental, and then my controls were using regular Ozorb with no palladium, which you wouldn't expect to see any catalytic degradation. And I also used it with just the reactor and no Ozorb in it at all, so that I could see, is TCE just kind of escaping through some hole in the top or something like that too. And so what we found here is with using no Ozorb at all, we do have outgassing, and that's the green here. And so that's the amount of TCE that's just lost with nothing in the vessel. And then in blue here it shows the amount of TCE reduction using just Ozorb, so no palladium yet. And then finally in red, where you see it going all the way down to the bottom, is when we put palladium in. And so the fact that there's a difference between when you have regular Ozorb versus palladium Ozorb shows that palladium Ozorb is able to first absorb the contaminants, but then catalytically change them into non-harmful species like ethane. So we established a baseline here for catalytic activity, and then we decided, okay, now that we know that catalytic activity is working, what can we do with this? And so we decided, let's try and modify palladium Ozorb. What can we do to it to make this happen faster, better? What can we do to this? And so one of the first things we did was we took the palladium Ozorb and we pre-rinsed it in a solution of ethanol. And what this does is you put the palladium Ozorb in ethanol and it kind of opens. So in this schematic here, it kind of shows how Ozorb opens and takes in contaminants. So what we're doing is kind of loosening the pores and allowing for the Ozorb to interact more with the water. Because when you typically put Ozorb into this little reactor, it floats on the top. It doesn't interact. But when you rinse it in ethanol, then it all combines with the water, and so you're having a lot more interaction of the TCE particles with the palladium Ozorb itself. And so we found that using an ethanol rinsed version of the palladium Ozorb, we found faster rates of degradation, and greater amounts of degradation of TCE. So this was a really cool conclusion to come from this. But the other thing that we would think about with this is, well, if it's open, are sulfur and other type species going to be able to get in easier as well? Probably. And so the next thing we tried was adding a polymer to the Ozorb. And so this is kind of shown here, where this is supposed to signify a palladium Ozorb particle, and then this little squiggly line right here is the polymer, which is going to go in and out of the molecule and kind of allow for the molecule to stay completely closed, but it'll allow products to get out once they're dechlorinated. And so we kind of figured that having the particle closed would mean that we would probably see less catalytic activity, because it wouldn't be as able to interact with the TCE. What we actually found was that it worked exactly the same. Everything almost overlaps exactly. And so that was another positive finding for this. So we did all this, and that was all great. And then all of a sudden we thought, when we're making palladium Ozorb, the palladium is probably on the outside of the Ozorb scaffold, because when we made the solution, there was extra palladium acetate hanging around in solution, and so we figured, oh crap, this is kind of sticking to the outside of the Ozorb, and so the catalytic activity that's shown here is actually not taking place inside of Ozorb, and it's just kind of on the outside. And then that goes back to the very beginning when I was saying you don't just throw palladium into water and look for catalytic activity. So we tried a different method where we filtered it. And so this is what happened when we filtered palladium Ozorb. We saw some really cool results, and the TCE absorption was really fast, and then degradation just kind of continued in a linear fashion. So it kind of made the calculation of the rate a lot harder, because it didn't follow first order kinetics anymore. So it still worked though. And so then, as I said before, catalyst poisoning is the main barrier to getting this established on a field scale. And so we did some studies with reduced sulfur species such as bisulfide and sulfite. And what I did here was I measured conductivity, because the reaction results in ionic species. So if you measure the conductivity of your solution, it's showing as the conductivity increases, I'm getting more ionic species, which means my reactant TCE is changing into my product, hydrogen chloride. And so these are both done on different levels of sulfur poisoning. And the fact that I'm still getting changes in conductivity, whether they're slightly inhibited, is really promising. And the fact that this one leveled off here is the fact that my conductivity measure only went up to 200 microsiemens per centimeter. So that one could have continued to go up. That reached our limit of detection. So basically the fact that we still have catalytic activity even after poisoning by sulfur is really promising. And finally, just another thing I did was with chlorobenzene, because another chlorinated contaminant other than TCE that's a big problem are PCBs. I'm sure you've heard about them. They're like endocrine disrupting chemicals and stuff like that. And so chlorobenzene is just going to be another similar analog to this. So we can see, can we also use these on PCBs? And so we saw largely the same kind of results, a lot of dechlorination, and so that was very promising. So in the future, we want to try modifying the palladium Ozorb with more polymers, like longer polymers, shorter polymers. We want to see what else can we do with this to enhance the capabilities of this material. And also we would like to just look at these on longer timescales, because each one of these is only 6 hours, but what happens in a week, what happens in a month, what happens in a year? So those are all things that can be done in the future, and hopefully will be carried on by students in the future years.
Not by you?
Unfortunately, not by me. I'm going to be passing it on. So sorry if I just talked your ear off.